webinar. Today we brought in Wade Webster, North Dakota State. He's a colleague of mine working in soybeans. Little background, if I remember correctly, he went to Montana State University as an undergrad, and then got his PhD at University of Wisconsin-Madison with a colleague, Damon Smith, working on modeling and things. And so we have the tar spotter app. He's built some of that data that's feeding it now moving forward. But I thought I'd bring Wade in and talk about his work on soybean diseases. So let's switch gears again. So welcome, Wade, and feel free to interact and ask questions. I think he's good with
Cool.
that.
Awesome. Well, thank you, Darcy. Wow. I was born in the darkness. All right. So, as Darcy said, my name is Wade Webster. I'm going to be talking about soybean diseases. I see there are a few of you that I convinced to show up today, so I appreciate that. If you are on the fence, I'm going to talk about some old diseases, mainly white mold within North Dakota, and then we're also going to talk about a new pathogen, new disease, frog-eye leaf spot, that is showing up in North Dakota as well. We're going to focus on primarily from a predictive modeling tool development side of this application, thinking of this from a farmer perspective of how can these tools be deployed and used by these farmers. So first, I'm going to take a little history lesson, and I'm going to see if any of you guys know this story, okay? But Purdue has a long history of football, right? We all know this. I'm sure many of you have been to the games, okay? But do you know where Purdue was started, Purdue football, when it was started? 1889, okay? And this was the roster of the team. There's one guy, Henry Luke Bali, who played the quarterback. He was actually the one who led the organization of the Purdue football team, the very first team to play at Purdue University. Okay. Henry Luke Bali grew up in eastern Indiana as a farm kid. Came here, went on to get a bachelor's and a master's in botany. Okay. Also played baseball, tennis, but went on to play football. Okay. After graduation with his master's in botany, he moved up to North Dakota. Okay. When he moved up there, he brought his passion for football, and he actually started the North Dakota Agricultural College football team. Okay. You can see him. He is in this back here. Okay. Right back here as the coach. And there's this story. Okay. He's a very passionate individual. Okay. In which the other team, University of North Dakota, strong rivalry. Okay. Even back in the 1890s, still is today. When one of the North Dakota players was running down the sideline. Okay, this coach, again, Henry Luke Bali, was so passionate, he ran out as the coach and tackled the guy. Okay, they still gave North Dakota the touchdown. Okay, now Henry Luke Bali then led this program on. Okay, is now a still pretty substantial program in North Dakota State University, NDSU. Okay, last year we won the national championship for Division I AA. Okay. In the past 11 years, we've won 9 of them. Okay. Again, because of this man, Henry Luke Bali. Now, Henry Luke Bali, when he went to North Dakota Agricultural College in the early 1890s, he was one of the first 3 faculty at the college. Okay. He then went on to become very prolific in the field of plant pathology. And so this is dating back, okay, the first 50 years of the American Phytopathological Society. And again, Henry Luke Bali is represented again on this document. Okay. He then went on, and this is actually really cool. And if you haven't been to the Arthur Herbarium, I think the herbarium still is here, I'm hoping. Okay. There's a sample in there. Okay. Puccini baliana. Okay. This is a rust of elderberry. Okay. That he collected from this region in Lafayette, Tippecanoe County. Okay. And Henry Luke Bali, one of your alumni from the department, collected this, and that is still in there with his handwriting still to this day. Okay. Now, while he was at North Dakota State University, there was a disease called flax wilt. Okay, what we now call flax wilt. And he went on to discover that this is actually caused by Fusarium oxysporum, and then led to the development of resistant varieties against this Fusarium species, preventing flax wilt, making North Dakota as a state the #1 flax producing state for much of the early 1900s. Okay. Just very, very influential here. To this day, we still have this one particular field outside of our research station that has had continuous flax since Henry Luke Bali first initiated that in the early 1900s. Okay. Again, going back because of the resistant varieties that he has had or developed, we've been able to establish ourselves in the state of North Dakota as a large agricultural hub. So just like the football team, okay, we also have our plant pathology team, and this is our list of our faculty within the Department of Plant Pathology. And I just want to highlight these individuals because I'm here representing that department, but everyone on this list is incredibly important for that team to succeed. Okay. Again, these are our was that 16, 17, 18 faculty members and our diagnostician that are listed in this particular figure. Now, for the state of North Dakota, we are a very diverse state, okay, especially with weather. And so this map here is showing the precipitation. The red color is lower precipitation. The darker green blue is higher precipitation. On the western side of the state, they're lucky to get 10 to 12 inches annually. Okay, so that's including snowfall, that's including precipitation during the growing season. Okay. There's been instances in which here they've gotten over 10 to 12 inches in a single day. Okay, so that is a very, very dry environment that growing is quite difficult. Now, on that side of the state, they have the Badlands, and they also have these open rolling prairies. Okay, so very different growing conditions than what we see here in Indiana. And then in eastern North Dakota, okay, in that southeast corner, only about 17 to 19 inches on average of annual precipitation. Okay, so while it is not the 30 to 40 inches that we see across some of the Midwest, okay, that's still substantially more than what we're seeing on that western side of the state. And because of this, eastern North Dakota looks very similar. Corn, soybean rotations. Now, as a state, we have a very diverse cropping system as well. Okay, I did the math, 17 crop species are grown. Okay. All of these, all corn, soybean, again, are high prolific crops that we grow. We also have a lot of small grains. That includes both durum and spring wheat that gets planted. We also have very specialty crops, sugar beets on the eastern side of the state. Very different because those have a different set of pathogens. Rhizoctonia especially would build up inoculum for some of our other pathogens. We have potato production at quite high levels, as well as dry beans, flax, sunflowers, canola. Okay, so very different. These farmers that I work with on a day-to-day basis, they do not have just a corn soybean rotation. Okay, they can move very easily between different cropping systems. Now, soybeans as a whole are not new to the state. They've been around for a while, but production has increased rapidly. Okay, since the 1980s, we've had an increase over 70 times. Okay, you can see that amount of production just exponentially growing, and it has started to kind of stabilize because we're running out of land to grow soybeans on. We're now on 7 million acres across the state of soybean production. That makes ours the #1 crop in the state, and it also makes us #4 in the US for planted acres. Okay. Now, from a production standpoint, the red coloration here is high. The amount of total bushels produced of soybeans, the lighter green is lower production here. And what you'll see are those two counties in bright red, Cass and Stutzman County. Okay, those are consistently #1 and #2 highest soybean production, okay, on a bushels harvested across the entire US. Okay, we grow more soybeans there than anywhere else in the country. And then why is that? And it's primarily driven because corn production is not as economically feasible as in the rest of the Midwest. Soybeans can hold up, but corn cannot. Okay, so farmers are preferentially choosing to grow soybeans. Now, with soybean production comes a long list of soybean diseases. Okay, many of us have seen some of these, okay, such as soybean cyst nematode, SCN. These are seedling diseases, Rhizoctonia, Pythium, Fusarium, Phytophthora. Brown stem rot, very much a northern soybean disease that we see inconsistently, but it's still present on a year-to-year basis. Phytophthora, root and stem rot, white mold, which we're going to talk a little bit about today. And then a new kid on the block is frog eye leaf spot. Okay, and so this is just a snapshot of some, but definitely not all of the soybean diseases and pathogens that we experience on a year-to-year basis. So white mold is caused by a pathogen, Sclerotinia sclerotiorum. Okay, I know you all have it within the state, and this is a very prolific disease because or pathogen because it can affect over 400 different species of crops. Okay, and almost every broadleaf species can be infected by white mold. Now, this particular pathogen, it needs cool nighttime temperatures and at least some level of consistent moisture in order to develop into disease and to form what are called apothecia. Now, these apothecia are small little structures, okay, that are developing from sclerotia. And these sclerotia here develop little cups. And these little cups that grow on that soil surface here, okay, what they're going to do with this sort of consistent moisture and cool temperature is that they are going to release bursts of apothecia or ascospores from those apothecia into the under canopy of that crop, okay? And why that's important is going to be discussed within our epidemiology and within the models that we're going to be talking about today, okay? So thinking about what is triggering those apothecia to form and release those spores. Whoop. Wrong way. So in order for managing fungicides, we do have to follow these particular rules that are laid out, okay? In each one, so rotating the fungicides into different fungicide groups, use the labor rates at the critical time points, okay? Limit the number of applications, so do not overspray, do not make more applications that are necessary. Educate yourself on what those fungicide groups are and the resistance associated with them or resistant risk. And then only select the fungicides that are effective for it, okay? Now, from my perspective, especially thinking from a disease prediction standpoint, we're only going to be focusing on these two, okay? Primarily looking at the critical periods of time to make these applications as well as limiting the number of applications, okay? And that's what these models that we're going to be talking about are going to be primarily trying to be driven. So there was a tool, or the previous models that were developed at the University of Wisconsin, Dr. Jamie Wilbur, who's now at Michigan State, was driving this, was the prediction of driving the environmental conditions driving the production of these apothecia seen here on the left-hand side. Now, what these models have done, okay, and there was a non-irrigated or a dry land and our irrigated models, very different microenvironments in both of those conditions here. Now, across that here, we're going to use this example of Hartley, Iowa in 2019. And this black line right here, that represents our daily risk level across the season. So that first black, at the beginning of that black line is at planting, the end of that black line is towards harvest. Okay. Now I have that R1 and R4 marked out, and that's what we call our flowering period or susceptibility window for white mold development. These ascospores need to infect into flower tissue to cause a successful infection. Now, we have this yellow line here labeled, and that yellow line represents our action threshold. These action thresholds have to be met, okay, meaning that that black line has to cross that gold line in order to trigger a fungicide application, okay? So in this particular case in Hartley, Iowa, no fungicide application was recommended during that flowering period. Therefore, that farmer should have saved that fungicide use, saving that individual money, not having that unnecessary application, okay? So these models were then introduced into this tool, what we call Sporecaster. And this is a smartphone app that we've developed, very similar to Tar Spotter, okay? This was actually the first situation of an app here for these models. And once you enter your particular locations, and we'll walk through this here in just a second, okay? And so by walking through this, and I'm going to see if this works here, it should. Okay, so this is the app on my phone right now. Okay, so this is what it looks like when you open it up, and I'm going to click New Field. So right now it tells me my current location is in West Lafayette. Okay, so I'm going to click on that map, And I'm gonna zoom out to a location where we work in called Oaks, North Dakota. Just south of there, we've got a research site, and I'm gonna drop that pin there. I'm gonna click done. I'm gonna name that site. I'm gonna say Oaks, North Dakota. In this case, I'm gonna put in the row spacing because we know row spacing is a factor involved in driving the development of these apothecia. So in this case, I'm gonna say 15-inch rows, so somewhat narrow row spacings. In irrigation was used. I'm gonna click done. And on here, there's gonna be a condition of are flowers present. Again, that R1 to R4 growth stage, that susceptibility window. So I'm gonna click yes. Now this action threshold, that's that gold line that I showed earlier. We can move that around, okay? If we want to say 35, we can do that. If we want to bump it back up to 40%, we can also do that. But we're gonna now select a date in which that is of interest. So what I'm gonna do is I'm gonna go to July 15th of 2024, around that time when soybeans are flowering, okay, and evaluate what that risk looks like. In this particular case, we are at high risk. Okay, this model, bright red, tell you high risk, go make a fungicide application at this point in time. Now I'm gonna bump this back down, say July 5th. And now we are at medium risk, okay? So maybe don't make that fungicide application yet, but if you're a farmer, maybe get prepared, maybe get the sprayer ready, maybe start thinking about, okay, should be making an application here in the coming days. You see this start to increase in time, okay? Now, you can back out to that main page again. You go to field list, and you can see all the different fields that are of interest to you. Again, thinking of from a farmer perspective, and you can also look at this on a map. So this is the state of North Dakota. These are each of the locations that I see, and you can see the color of that risk for that day. Okay, so this is a great way for these individuals to see their risk level across their farm and their operation. So one of the problems that we saw with these tools, okay, is that they were not validated across much of the Midwest or across the northern Great Plains up in North Dakota. Okay. These were developed Wisconsin, Michigan, a little bit of validation in Nebraska and Iowa, okay, but primarily around the Great Lakes region. We know these things work really well, but how do they work elsewhere? Okay. And so there were two different groups of models, are non-irrigated and are irrigated. The top two, so the top on non-irrigated and the top on our irrigated were shown to, or were the ones that were integrated into our app, the Sporecaster that I just showed you, okay? Now in North Dakota, we don't really deal with a lot of irrigated ground. We have some capacity, but not a ton. A lot of it is dry land irrigation. And so for the rest of this here, I'm just going to be introducing this as 1, 2, and 3, okay? Those are going to be the models that are represented. And so one of my graduate students, Sarita Pudel, part of her master's thesis has been the validation of these models across North Dakota. Okay? And two objectives in here are to validate that, one, they work, and that if they work, what action threshold should be used. Okay, should we move that gold bar up? Should we move it down? Okay. And so to do this, Sarita had for the past 2 years, 23 and 24, had been going around the state of North Dakota, evaluating and scouting for these apothecia presence in these fields, following this W pattern, again, between that flowering period of R1 to R4, okay? We then follow that up at the end of the season, towards that R5, after these flowering has ended, pods have started to develop, okay, grain fill is occurring when disease starts to develop. Now, by doing this, we're able to evaluate how severe of an infection occurred, okay, how much white mold was present, for what we call disease incident. Again, the percentage of plants that had disease develop. Then we took that disease data, the apothecia data, we aligned it with IBM weather data, okay, what we call from a company called the Weather Company, which is on a 2.5 kilometer resolution grid, okay. From a weather perspective, that is incredibly high resolution so that we can get site-specific, field-specific recommendations of risk level that are present. Within these models, they do use wind speed, temperature, and relative humidity. So those are primarily the variables that we are using here. And again, these are our three models, the non-irrigated models that are of interest that we're trying to validate here. Once these come back, okay, we have the logit. We need to plug the logit in so we can get a risk probability. Okay, a risk probability is risk of these apothecia developing again. Okay. So now this is an incredibly complicated slide that I'm really going to try to work through with you all. It's just a bunch of ones and zeros, right? That means so much to you all right now. Okay. So on the far left-hand side, what is field ID? Okay, those represent individual fields that were scouted. Okay, so right over here. Now that field ID, we went through 41 different locations across the state between those 2 years. And then we evaluated probability here. Okay, and then also disease incident here. So that probability is the highest risk level that was achieved during that flowering period. Okay, we don't care about what the average was, what the median was. Is at the highest, when apothecia could have developed, what was that highest level? Then disease incidence was again it was a percentage of plants infected in that field that was scouted. Okay. Then we calculated on a binary scale, so 1 or 0, whether or not disease incidence was greater or less than 5% or 10%. Okay. So in this first example, disease incidence was 55%, so it was greater than 5 and 10%, so both got a 1. Then we looked at that risk threshold. So same idea. Was that max probability percentage greater than 30, 35, or 40%? And if so, put a 1. If it wasn't greater than, put a 0. Okay. We were looked at actually from 20 all the way up to 50. But for simplicity of the slide, we're only looking at 30 to 40, as this is eventually what I'll show you worked out the best. Then was this success failure part. Okay. And so this first column, success failure at 5% of DI, okay, was if that DI at 5 matched with that risk threshold at 30. So if they were both 1s, they were in agreement. And so we put a 1 under that 30 for success failure. If they were both 0s, that's also a success. Told me the models did not say that risk was high and disease did not develop. So that's a success. What a failure is, okay, is when either recommended to make an application and disease did not develop, or the inverse of that, okay, and what we consider a failure. And these are listed here on the far right-hand side, both for disease incident at 5% and at 10%. From that, we're able to calculate an accuracy for each of these conditions of looking at disease incidence at 5%, 10%, across these 3 different action thresholds. And so in this particular case here, at 5%, highest was 73% at 35, and at 40% for 10%. Okay, those numbers are important, but just bear with me here. So we did this for each one of these models. Again, model 1, 2, and 3. Again, we have our DI percentages at the top and our action thresholds below that. Okay. Again, our 3 models, and these are the accuracy predictions from these conditions. Again, the highest that we saw was model 3 at that 75%, almost 76% accuracy at that 40% action threshold. Now, I'll remind you again, model 1 is what is currently in that app and is being used by farmers today. Okay. So that right there is a problem because the highest accuracy we got was about 66%. I'm not really happy with 66% accuracy. Okay. So this is all in fine and dandy, but then I thought, you know, let's see what more we can do with this data here. And so I looked at some of my weather friends, and hurricane season was coming around, and there's this thing called ensembling, what we call spaghetti models. And this is very commonly done within hurricane projection. Okay. Many of you have seen hurricane projections over time. You've seen that one band where that hurricane's going to go, but then all of a sudden, a day later, it shifts and it goes completely west, or it shifts and goes back into the Atlantic, right? So all of those projections, that one trajectory there is based off of multiple different models. Each one of these lines here is a different model. We have European models, American models, multiple different groups. And what that projection is the average of all of those models together. And so we took that same idea and took our three models and those risk levels associated with them, and we ensembled them. We took the average risk level for that and saw if we could increase that accuracy, okay? Again, for that final prediction or that accuracy. And by doing that, we were able to increase that accuracy, again, across 2 years of 2023 and 2024, and showing that that highest level of accuracy was 78%, okay, at that 35% action threshold. That's an acceptable level, okay? I'm pretty happy with that, especially in an environment that these models were not trained on. So the next step in that was taking it to a place where the farmers can utilize these data. And so we have a really great network in North Dakota called NDON, or the North Dakota Agricultural Weather Network. Daryl Richardson is currently the director and the state climatologist for the state of North Dakota. And each one of those dots represents an individual field or weather station that's set up in a field, okay? This map is actually not up to date because there is a lot more in Montana, and we have taken over almost all of Minnesota, okay? So that is what is considered our NDON weather network. We took our models and integrated them into this platform, the platform that farmers use, okay, across the Northern Great Plains heavily. And we're able to code out and give them daily risk maps for white mold risk. And so we can see again, red is high risk. That's when fungicide application should be applied. And when medium risk, blue risk is low. These are not silver bullets. These are tools that help guide when to make these applications. Again, that is our irrigated model, which was not updated from Sarita's projections. Again, we don't have a ton of irrigated acreage, and then irrigated with wide rows and seeing the differences there. Okay, and we're going to shift over to, that was the old foe. We're going to shift to the new foe, frog eye leaf spot, Cercospora saginna. Okay, this is something that has developed within the state. Okay, this is a polycyclic, foliar airborne pathogen that is primarily exclusive to the mid-south, the southern region of the U.S., a little bit of the southern Midwestern states. Okay, North Dakota should not have frog eye leaf spot. Okay, but it does. Frog eye leaf spot has been progressively moving north. Okay, in 2020 is when we had our first confirmation of frog eye leaf spot. Okay, it's 5 years ago. Now that was really substantial because we ended up finding that about a quarter of all isolates that we had are resistant to QOI fungicides. Even though we've never had this pathogen here, it is resistant because of producers in more southern regions that are making excessive applications of these products. Also the high risk associated with QOI fungicides leading to problems that maybe we don't have today, but problems we will have in the future because of practices that our neighbors have done. Now, frog eye leaf spot is again a disease that many of us have dealt with for years. And so there have been trials conducted, uniform foliar trials that Darcy is one that has been collaborating and sort of leading for many years. And so what we realized is that we have a large data set. We didn't use it for anything yet, okay, in this perspective, but we had this large data set just kind of sitting across universities. And so this student, Jose Gonzalez from Iowa State, who's been working with me on this particular project, has pulled data from each one of these individual collaborators in this project. And this is what the data or the field sites look like across the US from a frog eye leaf spot perspective, okay? We're having a lot of great coverage representative across the regions, a lot from the southern regions such as Louisiana, Mississippi, as well as quite a bit from the Midwestern US. 14 states to be exact, with almost 300 data points or site years of representative data for frog eye leaf spot that we are then using to develop new models, logistic regressions to base off in the prediction of when frog-eye leaf spot is going to be increasing as a cyclic, polycyclic pathogen throughout the season. And so what we found is that these two variables, the max temp and the total daily hours in which relative humidity is greater than 80%. Okay, so how many hours during the day is it really humid? That's what is the primary driver of this particular pathogen from our model. Okay. Just like our white mold models, okay, this is the important epidemiological biological factors driving disease. So Jose compiled all of this data. Okay, we had our university, and then we had one collaborator from a private industry who also supplied a very large, substantial data set of frog-eye leaf spot as well. So Jose compiled all of this, and then he went in and what's called data splitting. So you take, say, 300 data points, you take 70% of that, you set it aside, and you take the other 30% and you put it over here. On this 70%, you train your model, you develop the model, okay, get the math, the equations associated with it. And then on this 30%, what's called the testing is what you use to validate that model. Make sure that that model is accurately predicting what it's supposed to be. On top of that, Jose then created two separate data sets. He created just a university frog-eye leaf spot data set, and he created a university plus or industry data set. Okay. Now from that, Jose then went on to create different response variables. And that's ultimately what we are predicting. And there were two different, what we call delta positive, okay, in which disease increased between 2 time points. Okay, so whether from today, since last week, has disease increased, that would be considered a disease positive or a delta increase. And then there's another one called delta 5, meaning did disease increase at least 5% in the past week for that past time point. Okay, so it's looking at a severity or degree of increase of change of the pathogen. We then realized that we had a very large imbalance between our data set, meaning that we had a lot more zeros. Okay, a lot of cases in which disease did not develop, and a lot fewer, and not a lot, but we had fewer cases in which disease did develop. Within modeling, we would like that data set to be balanced. And so what we had done is we did what's called upsampling, is by pulling in those positive samples until we had a balanced data set, so that we had a 1-to-1 ratios between disease was present and disease did not develop in that case. From that, just like what we have done with white mold models, we then validated that accuracy. And this is listed here on the bottom. Okay, we created 8 models. And what I want to point out, this is somewhat small text here. Okay, but these 5 models over here, okay, or these 4 models from 5 to 8, these are our industry and our university models combined. And what happened is when we combined those, our accuracy dropped. Okay, which tells me that the industry data that we had included in there was not of high quality. Okay, we do not know who is rating these diseases. They could be agronomists, no shame to agronomists, but there's a lot of things that look like diseases. Okay, and frog-eye leaf spot could have been missed or could have been put on there for herbicide damage. Okay. Then when we look at just our university data, there were 2 models that came out with the exact same accuracy here, about 75%. Again, that's about our threshold for what we consider acceptable for pushing forward into the next step. So then the next step here was validation. Okay, we did do the validation with the splitting of the training and the testing data set, but we wanted to validate this within field trials. So Jose has been leading this particular project, okay, of looking at 5 different treatments. Okay, they're listed over here on the left-hand side. 1 is a non-treated, so we don't spray our soybeans. 2 is a standard application at R3. So that's just at the end of flowering, right as pods are starting to develop. Okay. And that's an application of Revitec, which has 3 modes of action of fungicide. Very effective product against controlling frog-eye leaf spot. Then the last 3 applications are adjusting those action thresholds again. So moving those gold bars. Okay, so we're going to have a low risk, medium risk, or high risk of that action threshold. Once we hit that is when we make an application. Okay. And so what we developed is that this medium risk, that 50% is where we found that 75% accuracy. So again, should we increase that or decrease that? So within this, we again had 13 states. Many of our collaborators across the US have run these trials for the past few years. Okay, and in 2024, we had 20 sites with this particular model. Now, all of these are evaluating for frog eye leaf spot severity, which was then calculated into area under the disease progress curve, or AUDPC, progression of disease over time, and then also yield. And so this is, again, the tool very similar to our Sporecaster. Jose went in every day, every location that we had, and he evaluated. Okay, are you at the threshold? Or are you not? If you were, he'd text you and say, hey, you need to go make a fungicide application today. Okay, on a weekly basis, he'd remind you. He's like, hey, don't forget, you've got that trial out there. Remember, it's really important to his PhD. Jose recorded that, and he must have listened to this. That's funny. I did not know that. All right. I kind of want to go back and listen to it for a little bit. Funny. We're gonna have to text him that later. So what he found is that these treatments had effects on disease development, or that AUDPC at 5 locations across those 20. Okay, we would expect this. Some locations had low risk, some didn't. But again, is these pink bars or salmon colored bars here, that is our non-treated. You can see just how high those AUDPC values are. But by making these applications, the green bar is our R3, our standard application, and then the blue bars going from dark blue is our low, lightest blue is our high action threshold. Now, examples like this Princeton here of that R3, okay, we know that R3 is our standard. That's what we're trying to match, right? Okay, so right here, we see this R3, our low and our moderate action threshold worked fairly well. But then once we got into this high action threshold, maybe that application was a little late. Okay, maybe we should have made it just a little bit earlier. Okay, and obviously it takes time to go from a 50% up to a 60% action threshold. Okay, so these are examples that could be explaining when these applications should be timed up. And obviously there are going to be environmental differences between each site here. Now, these are the locations that were applied, okay? The state, the site, and then that threshold met, okay? That indicates which of those thresholds were met. Not every site had those thresholds met, okay? And quite a fact, many of them across the Midwest did not have them be met. The ones in yellow represent the locations that did have them be met. So again, we have our Oaks, North Dakota, which of course just happened to be where I am. Okay, and then 3 in the southern US, Louisiana, Mississippi, North Carolina. Why is Oaks, North Dakota like the southern US? I have no idea, but through our models, that's what it looks like. Okay, very humid during the summer, but very distinctly windy, I can tell you that. The rest of these did not have all those action thresholds met, okay, which indicates to me and Jose that maybe we should be thinking about these as a regional differences here. Okay, maybe the southern US should not be grouped with the rest of the Midwest. Okay, and so that was kind of the next step, and that's not, we don't have that done yet. Jose's working on it this spring and winter, trying to get that wrapped up for his dissertation. Now, the last thing is treatment effect on yield. We did see some treatment effect on yield, in which again, these non-treated having the lowest yields, except for this Columbia, Missouri location, in which these fungicide applications had lower yield. Don't know why. But again, we are seeing some treatment effects due to these applications, hopefully trying to tease out some of why these models can be effective from a production perspective. Across these validation trials, okay, this is looking at the sensitivity, which is what we call our true positive rate. So when they're correctly predicting when disease is going to develop, and our specificity, which is our true negatives, correctly predicting when disease is not going to develop. Then we also assess our accuracy. And so what I take away from this is that 50% had fairly good specificity, the highest sensitivity, and it had the highest accuracy. So I feel very confident at this point deploying these models across the US or across at least the Midwest, okay, but from our data set across the US is a tool that farmers can use. And so now I'm going to show you this. This is actually really cool. It's very new. This is the live version. If I can get the internet in here to, there it goes. So this is a new crop risk tool. So I've showed you apps that we've been using, but now we have what's called a one-stop shop. We have all of our models in one place, okay? And what this is going to ultimately be is hosted on Crop Protection Network, okay, which is an extension resource for all the extension specialists across the US to put in their field crops information. And in this location, or in this map here, okay, you can scroll up, you can move around whatever fields you're interested in. So again, I'm going to go down to that Oaks site, or at least close to it, okay? So I'm going to click right just a little bit east of Oaks. You can put in multiple locations in here at the same time, but you're going to have this start date over here as well. And this start date, you can move back in time, okay? So I'm going to go to 2024. Again, you can look across the entire season. And so I'm going to go May 1st through the end of September of 2024. Okay. Then I can click fetch weather for that particular location. And when I do that, on the right-hand side down here, okay, we can see gray leaf spot on corn and tar spot on corn. And we can see that season-long movement of risk, okay, for that particular crop and that disease, which is really useful, especially for a farmer or a researcher that's interested in these tools or these diseases, if you can see that risk. You can then go over to soybean, and we have the same thing for white mold and our frog eye leaf spot models. Again, you don't have to have two different apps. You can do this in the exact same location, see them together. Are they moving or are they not? For white mold, I just showed you the dry land models are different than the irrigated. And so we have a little tool there and we can drop that. So in this particular site in our dry land for that Oaks location, we didn't see risk, but in irrigation, which this site is, again, during that flowering period. So around the beginning of June, we start to see it jump above that action threshold, getting into that high risk environment. We also have other models integrated in. These are coming from the University of Wisconsin vegetable production group for potato and tomato for early blight and late blight. We also have alternaria leaf blight on carrot, and at the moment, Cercospora leaf blight on beets. Okay. Eventually, what we hope is to have more of our models integrated into this tool so that we can use this, again, from both a research perspective and from a production perspective here. Okay, so I'm getting up close on time. I'm not going to go into much detail on these slides, but I do want to just recognize the other individuals within my lab program and their research projects. Okay, so I presented a lot on these predictive models, but we do a lot of other work as well. So Medea Matlub is one of my PhD students who's working on biological control. She is primarily focusing on the isolation of biocontrol agents from bulk soil. So not associated with plant, but species that could potentially survive in environments without a plant. Okay, we want these pathogens or these organisms to be able to survive multiple years in that soil to fight off pathogens that are present. Okay. And she has done incredible work looking at 3 different pathogens against Rhizoctonia in that bottom left-hand corner. Okay, you can see what's called this inhibition zone down here against dual competition assays. Macrophamina phaseolina having this really great inhibition zone of some sort of secreted metabolite, and then against Sclerotinia sclerotiorum. She's also done this on detached leaf assays. Okay, many of these are not foliar pathogens, they do not translate like this, but what we're trying to confer is that some of these biologicals may not be exuding chemicals, but they may be having a host response. Okay, and that example on the bottom, you can see that control is our positive control, or our negative control actually in this case, which is infected with Sclerotinia. You can see how much development of programmed cell death and a essentially lesion developing, but on our biological control, with the plug of sclerotinia on top, we see no disease development whatsoever. So what that's indicating to me there is that there's some sort of host response. That pathogen or that organism is triggering something in that leaf and not allow it to develop. There's another PhD student, Rachel Konchak. She's looking at, one of her projects is looking at the evaluation of oomycete populations across the state, looking at primarily Phytophthora, but also the other Pythiums, Phytopythiums, globus pharyngiums. One of the key findings that Rachel has found in the past few weeks actually is that we have confirmed and fulfilled Koch's postulate of Phytophthora sanzamiana, a new Phytophthora species to North Dakota, not new to the rest of the Midwest, but an issue that we think could be more of an issue than what is previously discussed, meaning that our traditional resistance genes and varieties are not effectively managing. We have a master's student, Rachel Yum. She's looking at development of a multiplex PCR for root rot pathogens associated with the plant diagnostic lab. And she's a really interesting situation in which she came in right out of undergrad, knew she wanted to work in a PDL. Okay, nothing was going to change her mind. She wanted a project that could develop or that could benefit the development of a tool to help the diagnostic lab. Okay, and is leading that charge, trying to distinguish between a lot of our Rhizoctonias, Fusariums, and our Pythium Phytophthora species. Another master student, Vanessa Laux, okay, farm girl from southern Minnesota, wanted to do farm research, wanted to understand things that she could take back home and help her dad and grandpa on the farm. Okay, one of the things was seed treatments. She wanted to compare against multiple commercially available products across the state of North Dakota. Okay. And she has been doing this both from a fungicide perspective and an insecticide perspective, looking at different root feeding of different insects. And she's found, to no surprise, that seed treatments are very highly effective across eastern North Dakota, where we have high moisture, lots of pathogen pressure, lots of soybean production. But in western North Dakota, we actually see some sort of phytotoxicity generally across our seed treatments, in which we are seeing lower yields associated with seed treatments comparatively to a naked soybean seed. Okay, that's interesting. I don't know what's going on there, but it's very consistent. And then finally, this is my research assistant professor, Hope Becton, and she is, one of her projects is looking at development of logistic regression models for stem diseases on soybean as well. So stem canker, charcoal rot, pod and stem blight, and a anthracnose and brown stem rot. So with that, I'm a very large human and my lab is not okay. So this always gets chuckles. But I think I have a student starting in August that's at least like 5'11". So I'm hoping that picture won't look as dramatically different. But thank you all for coming today. I really do appreciate it. Thank you, Darcy, for the intro. Yeah, Christian.
Practical question here for, I believe that you say the sensitivity in one of the examples was the lowest compared to specificity and numbers. So I guess that the question is, what do you wish you had to continue improving that? Because obviously any model requires improvement, right? So is that because of representation of the positive force data?
Yep.
How do you interpret that?
Yep. So I interpret it as we need more high quality data, especially from a positive disease incident and severity. So a lot of times frog-eye leaf spot as a disease looks very similar to many other things. We have a lot of other herbicides that cause very similar looking damage. Disease severity could also be hidden but below that top canopy of the soybean crop. There's just a lot of error associated with frog-eye leaf spot as a disease. It's not very cut and dry. And there's also this thought there that frog-eye leaf spot could be potentially inhabiting that leaf tissue without having external symptoms developing. And so I think that there could be possibilities there that are driving that sensitivity down. And again, we just need more high quality data from trained pathologists with positive frog eye development and not more zeros. Yeah,
That's always a challenge. Always zero.
constantly, I know.
Yeah.
That's you. Yeah.
Have you ever thought about looking at it or addressing it from a histological perspective? Maybe.
No. That's a good thought, though. Be, if I had more people to do the work, then, yeah.
Or you could always collaborate with.
Yeah.
RC or.
Oh, absolutely. Yeah. Yeah.
Yeah, genetic resistance
For frog eye, yes, and that, yeah. Yes, there absolutely is resistance to frog eye. And it, RCS genes are primarily qualitative resistance genes that are available. And depending on where you are in the country, these resistances are well characterized and well labeled on seed variety bags. So in North Dakota, frog eye leaf spot is never on a seed variety bag. No farmer is ever looking. No seed dealer is ever pushing that information. It's just not available. So we don't know what a lot of these varieties are. And that's actually one of the points that could improve these models, is if we could integrate in resistance into them, then we could potentially circumnavigate that. Now, I had done some work actually during my PhD looking at the Sporecaster, the white mold models. And what we found is by adjusting those action thresholds based on those resistant packages from a quantitative perspective, not qualitative. But if we have higher levels of resistance, we can actually move that action threshold up. If we know we have a very susceptible, we can move it down. So I think of it as like a post hoc adjustment to those models and validation of those tools.
Another piece of question, is there a case where the disease risk is high for one pathogen, but then low for another one, contrasting? Is there a case like that?
Yeah, yep. So gray leaf spot and tar spot are actually that example. And so if I can. Gonna reload. But yes, that is absolutely the case. And it primarily is driven by, tar spot as being such a prolific disease, right? Farmers are going to be making applications for that. Gray leaf spot, maybe not so much, right? Depending on where you are within the country, right? So again, these are not silver bullets. These are tools that help guide risks and management of these tools, or of these particular diseases that are developing.
So there are them being complicated parasites or not, or like transport obligate?
So not so much. It's just the environmental conditions that are driving, right? So if you look at rust across the wheat, right? So we know striped rust and stem rust are wildly different environmental conditions that are driving those different pathogens. So the management strategies are going to change depending on which one you're targeting, which one you know is a consistent threat, right? Farmer in North Dakota is never going to spray for striped rust. We get it 1 out of every 10 years, right? But stem rust, maybe 1 every other 2 years, you might have it present. So there's just kind of, again, suggestions helping to make those data-driven decisions on the farm. Yeah.
Why does it seem like any plant pathology models ever use growing degree days, as our entomology friends do?
Because great question. So that's primarily driven because these pathogens are much more complicated by reduced growing degree date. If that were the case, you would do it, right? It's incredibly simple to put in growing degree days and try to track that development.
I realize you would have to do it with moisture and with humidity as the extra factor, but one of your factors in there is 30-day average maximum eye temperature. That just sings to me that perhaps we could use growing degree days as another, as something.
It could, absolutely. And, very similar point, that is kind of fitting that value to it. It is it is something that I guess could be added in within our data set of our weather variables that we're using to develop these tools. It wouldn't take much. It's just a simple adding it in as an extra line. But again, just very, so when we do it, we do have within what's called a window pane. And so for each weather variable we'll take the mean, min, the max. So air temp, precipitation, wind speed, relative humidity, and we take that across different time ranges. So the 30-day moving averages, very similar to growing degree days, or at least from a temperature perspective there, okay, is that we can then shorten that down from 30-day, 21-day, 14-day. We can back that down, increase that moving average over time. And so we do have, each model is trained on about 200 different variables, or 200 different environmental variables are assessed for their impact within these models. So it is something that could be easily just introduced in the system. Right.
So when you're showing that risk for tar, for example, it went up and it went down, is that risk for like an epidemic establishing, or is that progression of the epidemic, or what does that risk mean?
Yep, so that risk means that a new tar spot severity has increased between time point A to time point 2. So what that means is that a high risk that tar spot is going to be causing new infections.
Gotcha.
And so from an epidemiological perspective, does that mean there's going to be spore flight? That mean initial infection? We don't know at that point. And so this is what we call field epidemiology. And this is not in pure sense epidemiology of understanding each portion of that disease cycle. That's part of where we want to get to with some of our spore flight sampling. So over the past few years, a lot of the extension specialists across the US have been sampling for spores and spore traps, quantifying those on qPCR, trying to understand what environmental conditions are driving that flight of new spores and that first flight of spores early in the season from crop residue.
Gotcha.
So-
An ongoing thing.
Is an ongoing thing that we're trying to tease apart all of these impacts, yeah.
The data that is fed into these models, do you ever take into account the cultivar or varieties of the crop itself because of the potential tolerance or resistance to the disease itself, or could that lend to some of the inaccuracies in the data that you have?
Yes, so no, they are not, primarily just because we don't know what those levels of resistance are. And so the quantitativeness of different resistance to pathogens, white mold, for example, tar spot is another great example. That resistance is not characterized. And how do we separate from Darcy's data that shows one hybrid as being moderately resistant comparatively to Illinois, maybe showing it moderately susceptible? How do you code that out? Right, it's quite difficult when you have that G by E interaction going on. From a qualitative side, that could be coded out, but then you would be dealing with examples of, say, resistance breakdown of those particular resistance genes. And so what we've been able to do is just look at them as after the development of these models, can we then adjust the action threshold so that we can account for that resistance level within that variety.
Most of this, I would say, did most of our trials of target to plant a susceptible variety or whatever, so that was part of the protocol.
Yep, so
What something susceptible out, or what we could.
true, what we
Right,
knew,
initial stuff.
what we thought could be susceptible, and it is always kind of a game, especially soybean and corn's the exact same way. These varieties and hybrids, they come into the market and they go out of the market in about 2 to 3, 4 years. So if we know we have say for white mold, we have a really susceptible variety of white mold, we try to get as much of that as we possibly can so we can save it for the foreseeable future. Okay, and generally, and I'm not sure how Darcy does this, but what I'll do is I will call one of our seed dealers. We work with a company called Peterson Seed, a regional seed breeding company. And I'll call up my guy Rick, and I'll say, Rick, you got to tell me, and I won't promise, I won't tell anyone, but what variety is just terrible on white mold? I need that, and I need a lot of it, right?
They ever
So-
laugh in your face with that? You have to go.
Usually no, they're always like, hey man, you gotta not tell anybody, I promise, this is really important stuff, and I say, I won't, I promise. And I get them a beer afterwards and it's all good, but that's generally how it goes for finding resistance. It's not, we try our best to make things susceptible, so we understand again from a disease perspective, disease development perspective, that's how these are developing at a biological level.
Any more questions? We're out of time.
So what level of resistance are you describing for white mold?
Okay, so white mold, white mold resistance is highly quantitative with no major effect QTLs whatsoever. And so it is a disease that we know that there is high levels of resistance available commercially, but there's not many varieties out there. Now, how to rate that would be incredibly difficult. What we've done is we have developed a set of what we call check lines. So we know this particular line is very resistant. We know this one is very susceptible. We have two right in the middle. They kind of swing moderately susceptible, moderately resistant. And what we can do is we can then assess any commercial varieties comparatively to those check lines and then give them a rating: resistant, moderately susceptible, or susceptible based on that. But again, that goes back to the G by E. These things can change wildly across the environment just because of how quantitative this resistance is, this clearing. Cool. Thank you.